Hi, this is IC Engine Lab report with Drew Mallott, Francisco Solares, and John Wheeler. The goal for this lab is going to be determining the system parameters for simple systems like torque, inertia, friction, and work from this motor, and the control generator to optimize the IC engine. The way we're going to solve for these system parameters is going to identify simple systems and make small experiments that will help us determine each one of these ones. This is the motor, and it's a 4-stroke engine with intake, compression, power, and exhaust, and it runs with an electrical motor. And for the data collection, we're going to use an encoder that detects crankshaft position at each 10 degrees and the relationship between rotation and linear position motion. At the same time, we'll use a force transducer that measures change in resistance via a Whetstone bridge, signal conditioner through a series of amplifier, and some noise removed through low pass and band pass filter.
Okay, moving into week one, the simple system we used was removing the engine head and just having the engine powered by the motor. We collected some physical engine dimensions, and we collected the data with and without flywheels. We are finding the work done by the motor during steady state, the frictional torque at each RPM, as well as the work done by the motor to accelerate the flywheel or flywheels. And then finally, the flywheel moment of inertia. As far as calibration, we put incremental weights on the force transducer and scale and then collected that data. So we got the calibration equation. With that calibration equation, we were able to collect data. At low RPM, some of the effects that we noticed between the different sizes of flywheels or different number of flywheels were we had more output from the work in a 4-flywheel case, and then higher inertia as well in the 4-flywheel case, which is expected from theory. There was also more work from friction in the 4-flywheel, and as well as the overshoot in the angular velocity, as can be seen in the plots. In the 4-flywheel case, we believe that it's more efficient because the difference in work of the motor and the work of friction is larger than in the case for 1-flywheel. Moving to medium RPM, everything had stayed the same aside from the work from friction. There was more work from friction in the all-flywheel case or the 4-flywheel case, and that can be seen in the graphic for velocity as well. And this time, instead of having a difference in efficiency, they were pretty similar between the 4 and 1-flywheel. For the high RPM case, there was more work output in the 1-flywheel case for this situation, which is a little bit confusing, but something that can be looked into in the future. And additionally, there was more work from friction in 1-flywheel, which had changed from previously. As far as conclusions go, some of the things we were thinking about were frictional torque. The change between RPM is significant enough to say that it's a Newtonian friction model, so the friction changes from RPM. And the frictional torque is unchanged based on the number of flywheels, which is a good thing. Less flywheels mean a faster time to steady state, which is apparent in each RPM run. And then there's higher work output from more flywheels at low RPM, but the opposite at high RPM. And then overshoot was higher in the 4-flywheel, which makes sense because of the mass or the inertia from the mass, the added mass. And then it appears that 4 flywheels are more efficient overall. And then finally, the moment of inertia values are similar over the different voltages, which can be seen in the table below. There was a 6% difference between low and high RPM, which is good enough. And then but the difference, unfortunately, in the theoretical and experimental was very high, around 100% between the flywheels. This could be error and noise in the encoder measurements, and it does have a pretty large precision value. So that could be something that caused that.
All right, what did we do week 2? So we put the engine head back on the assembly, and now we're considering work due to the piston movement, work due to the air pressure, and trying to characterize like a representative 4-stroke cycle for the engine. So first we recalibrated our torque transducer. Here's our calibration data and the resulting linear calibration function. Why did we do this again? The sensor has air and it has zero drift, and this seems to change in between whenever we go into the lab. So we want to calibrate each time to fix this issue and just increase our overall accuracy. With 4 flywheels on the engine, we made a representative cycle. Here's the torque versus angle. So this was done by segmenting the data and averaging each cycle into this chart. And let's take a look here. So we have the, can I get a pointer? Laser pointer. All right, we have this is the intake, stroke, compression, power, and exhaust. And we have the low RPM, medium RPM, and high RPM shown. So we believe that the smoothing of the data might have shifted these a little bit, these troughs, which should be more on this black line, but we need to investigate that further. For the 1 flywheel cycle, here's the representative cycle graph for the torque. So using that data, we can calculate an experimental value for the work of the air, and that uses this equation. And we can compare that then to a theoretical model. The assumptions used in that are that the compression happens quickly and it's adiabatic, that the pressure at the bottom stroke is 1 atmosphere and a specific heat ratio of 1.4. And doing that math, we get that the power stroke should be 22.22 newton meters of work, and the opposite or negative value for the compression stroke. And this is the equation for the experimental work due to the air. And when we calculate that out for the 4 flywheel case and at each RPM, and for 1 flywheel case at each RPM, these are the values we get. And you can see the discrepancies between them and the expected values found by the theoretical model on the previous slide. And let's see, we see low discrepancy for the 4 flywheel case in the compression stroke, much higher discrepancy for the 1 flywheel case. We just got this data. We're not totally sure what to make of it, but we are still analyzing. Yeah, the data has a lot of noise, and we are currently experimenting with different techniques to smooth it and kind of looking at how that affects the work due to the air. Yeah, I already mentioned that the 1 flywheel case shows less discrepancy in power, but more in the compression stroke. And for the 4 flywheel case shows less discrepancy in compression and more in the power stroke. And there appears to be more work loss at the lower RPM cases. Next steps are to find a better way to filter the data. As I mentioned, I think our smoothing techniques might have shifted the data in the representative cycle, which is throwing off the work due to the motor values that we use to calculate work due to the air. So we need to look into a better way to filter or smooth that data. We also want to build a better control parameters for the compressor and begin to write the report. We referenced lecture 9 from this class. All right.